Okay, welcome back everyone. We are calculating the shadow of Kerr black holes. So that's the kind of picture we could see in the movie Interstellar, right? Remember, there was a very carefully calculated image of the shadow of a Kerr black hole. And I'm afraid I have to write a few equations again. So we would need at least the theta and the r component of the equation of motion. I will need this again today. So I have to write it again. So this was rho to the 4 theta dot squared was k, Carter constant, minus L over sine theta, minus A over C sine theta e squared. And rho to the 4th r dot squared was minus k delta plus r squared plus a squared. What letter is this? I cannot read my own handwriting. It seems to be an E. E over C minus AL. Okay, and well, we're looking for spherical light-like geodesics. Geodesics, light-like geodesics, that's only for light-like geodesics. Yeah, for time-like and space-like ones, we have the terms with the epsilon here. So we are looking for geodesics, light-like geodesics, which stay on a sphere. So we need the equations r dot is 0 and r double dot is 0. This will give us geodesics which are confined to a sphere r equal constant. And these two equations could be solved for the constants of motion. And if one does it properly, unfortunately I produced a mess on the board, but if you do it properly, you find that k over e squared is 4 e squared, r squared delta, divided by r minus m squared. That's 1/2 the derivative of delta with respect to r. Yeah? So you could also write for this expression r minus m 1/2 delta prime, if you like, times c square. And for L over E, you get A times L over E is 1 over C, or let me write the C on the other side, r squared plus A squared minus 2r delta over r minus m. So that's the equation which we will need in the following. So if we have a spherical light-like geodesics on a certain radius value r, then the constants of motion which are corresponding to this geodesics are given by this equation. This equation doesn't tell us for which radii actually spherical light-like geodesics exist. It just tells us what the constants of motion are. If we want to know at which radius values such geodesics exist, we have to make sure that this expression here is non-negative. So we have to plug these expressions for k and for L into this here on the right hand side into this expression, and to require that this is bigger or equal than 0, because the square cannot be negative, a square of a real quantity. And this gives an inequality, so it gives what we call the photon region, the region where actually these spherical light-like geodesics exist. And the inequality reads, again, if you juggle a little bit around with the terms and write them in the most convenient way, you get something like that. 4r squared delta must be bigger or equal than rho square r minus m minus 2r delta squared. I think that's the most compact form in which you can write this. So you see, for a equals 0, it becomes an equality, because a square cannot be negative. So if a is equal 0, then this expression must be equal to 0. And if you plug this in, if you plug the value a equals 0 on the right-hand side in, you find that this is satisfied at r equal to m. Yeah, it's a Schwarzschild horizon. Sorry, r equal 3/2 Schwarzschild radii. It's a photon sphere. But in general, it's not just a sphere, not something two-dimensional. It is really a region, yeah, something three-dimensional in space. And I already draw a little picture how this region looks like. So if you have a black hole which is not static, which is actually rotating, and you get something like that. Here's the horizon, or the two horizons, And then you get a region like that. So let's call this K. Let's call this region K. And the region K looks like that. So we will discuss in the next worksheet where they are actually circular light-like geodesics. So the condition that they stay on a sphere does of course not mean that they are circular. Yeah, they can move around on the sphere in a very complicated way, and they do actually. So what they do in general is they oscillate between extremal theta values up and down, and they also have a phi motion, of course, which may even turn back. So that it is prograde for a certain while, and then this happens, that it turns back and then becomes retrograde. So the phi motion is quite complicated. But some of these light-like geodesics are actually circular, and we will do this in the next worksheet. We'll find out where they are actually circular light-like geodesics. And there are precisely 5 circular light-like geodesics. Yeah?
Well, I have a question. So this R coordinate this is actually not the circumferential radius. It's just so to say coordinate radius. It doesn't represent a sphere. Yeah.
Well, the question was about the geometric nature of the R coordinate. In the Schwarzschild case, of course, it is the area. Yeah, and the Schwarzschild coordinates really gives the area in the form 4 pi r squared. This is not true in the Schwarzschild case. So it is not what in geometry they call a round sphere. Yeah, really a sphere with the induced metric which comes from the standard Euclidean metric. In geometry this is called a round sphere. So, but it is topologically a sphere, of course. Yeah? It's a sphere with a more complicated intrinsic geometry, but it is topologically a sphere. And if you ask me by what property the R coordinate is distinguished, among other things precisely by this property, that these light-like geodesics stay on spheres in these coordinates. Of course, in other coordinates that's not the case. Yeah? They stay on topological spheres, but they have a much more complicated coordinate representation. So these Boyer-Lindquist coordinates are really particularly well adapted to the symmetry. You also see this from the fact that the Hamilton-Jacobi equation separates in these coordinates, not in any other coordinates, just in these coordinates. So they are distinguished by the symmetry. Okay, so this was what we did last time, and now we want to calculate the shadow. So we have this region now, and now remember how the shadow was constructed in the Schwarzschild case. In the Schwarzschild case, this was just a sphere, r equals 3/2 Rm, or r equals 3 times little m in this notation which we use now. And then we fixed an observer somewhere. We fixed an observer at some position. And we distinguished 2 classes of geodesics, light-like geodesics, which arrived at the observer. The ones which moved towards the horizon, if we followed them into the past, and the ones which were just deflected and then went back to infinity. And the borderline case between the 2 cases was given by light-like geodesics which spiraled asymptotically towards r equals 3m. So what will happen if we are now in the Kerr case, where we have no longer the photon sphere at r equals 3m, but this photon region? What we expect is that the boundary of the shadow will correspond to light-like geodesics which spirals towards one of these spherical geodesics, and that's precisely what happens. Yeah? So this region K plays the same role which the sphere r equals 3m played in the Schwarzschild case. So if we want to calculate the shadow, what we have to do is we have to classify the geodesics, the initial direction for geodesics, according to the property, do they go to infinity or do they go to the horizon? And the borderline case between the two, this gives about the boundary curve of the shadow. That's what we want to calculate now. The situation is now more complicated than in the Schwarzschild case. In the Schwarzschild case we had spherical symmetry, so what mattered was just the angle theta with respect to the radial direction. Yeah, everything else was irrelevant. Yeah? And it was clear from the beginning that the shadow would have to be circular. Here we have now the spherical symmetry broken, so it will not be sufficient to characterize the initial direction by just one angle. We will really have to parameterize the whole celestial sphere. And there will be no rotational symmetry of the boundary curve. So we have to introduce celestial coordinates for the observer. So how do we do this? We want to characterize all initial conditions for light rays. Yeah, according to, we want to parameterize them by celestial coordinates, theta and phi. theta and, or I should call them big theta and psi, in order to distinguish them from the coordinates on the base manifold. Yeah? So how do we do this? Well, we need to introduce a certain basis at this point, 4 linearly independent vectors, and we write the initial direction of the light ray as a linear combination of this. So if we have a light-like vector k at the position of the observer, so k is a light-like vector, it's tangent to a curve, so I can write it in the form r dot dr, let me begin with t dot dt plus phi dot d phi plus r dot dr plus theta dot d theta. And then I also want to develop it in terms of a certain basis, which gives me the parametrization of the celestial sphere. So I introduce a time-like vector E naught, time-like unit vector, which gives me the initial direction of the velocity vector of my observer. And then I have E1, E2, and E3. Actually, the E naught is a time-like vector, so this is a purely spatial picture, so it should come out of the board. It's a little bit difficult to depict this. So think of this coming out of the board of the E naught. Yeah, and in the board, which is actually something three-dimensional, we have E1, E2, and E3. So then I have, if I have fixed this basis, I tell you in a minute how I choose this basis. Then I can write everything as a linear combination of these 4 basis vectors. I should leave space for coefficients that way. So, okay, and how do I do this? I want to have path pointing light-like vectors, so I choose a future pointing E naught, and I put a minus sign here so that it goes into the past. And then I have, what did I do here? So remember how the spherical polar coordinates on the sphere are introduced. If you have a x, y, z axis, or E1, E2, E3 axis, how the spherical polar coordinates which parameterize the sphere are related to the spaces. So you have cosine of theta here. I use a capital theta to distinguish it from the theta on the base manifold. Then I have here sine theta cos psi. Psi is the azimuthal angle on the sphere. And I have here sine theta sine psi. Okay, so this gives me a light-like vector. Yeah, if E1, E2, E3 are orthogonal to each other, orthonormal to each other, and this is a unit vector. And if E naught is a time-like unit vector, then the whole thing is light-like. Yeah? And because I don't know if this is actually, I know that this is also a light-like vector, but I don't know that the projection to E naught is just given by 1, so I would need a normalization factor here. Yeah, just a factor in front of this. So whenever I choose an orthonormal basis at the observer, I can write my tangent vector in this form. And this gives me coordinates on the celestial sphere. So just a second. So theta equals 0 is in the direction of E3. Yeah, theta equals 0 is a pole in the direction of E3. So you might should point it in this direction. Yeah? If you choose E3 upwards, then theta equals 0 goes in this direction. So theta is this angle. Theta equals 0, pi half, pi. And then I have an angle psi, which goes around this way. So it's the usual kind of coordinates on the sphere. And there was a question?
Shouldn't it be big theta in the E2 component?
Yes, of course, thank you. It's the same thing everywhere. Okay, I try to distinguish this theta from this one in the following. Okay, and now I can choose this basis as I like. So this would give me the celestial sphere of the observer parameterized in a way adapted to the certain 4 velocity. How should I choose this 4 velocity? Maybe your first idea would be to choose E naught just as d by dt and then normalize it so that it is a unit vector. But we have seen already that d by dt is not time-like everywhere. It fails to be time-like in the ergo region. So that's not a good choice because this wouldn't allow our observer to be in the ergo region. And maybe we are also interested in having the observer inside the ergo region. So d by dt is not a good choice. Then we had these zero angular momentum observers perpendicular to the t equal constant surface. They are time-lag everywhere, but actually they are not very well adapted to the symmetry. So the formulas become not very convenient if you choose them. You could choose them, but they are not very convenient. The most convenient choice is to remember what we learned about the ingoing and outgoing principal null directions. Remember, we did this on Tuesday. We discussed light-like geodesics which generalize the radial ones. Yeah? Which in the case of no rotation, in the case of a equals 0, reduce to the radial geodesics. But in the spinning case, they deviate from the radial direction. There are no radial light-like geodesics in the spinning case. So they span at each point in space-time a two-dimensional subspace. Here's the outgoing one, the ingoing one. The two-dimensional space with signature plus minus. And there's precisely one linear combination of d by dt and d by d phi, which is inside this plane. Yeah, so what we choose for our velocity E naught is a unique time-like unit vector, which is in the plane spanned by the principal null directions. This will give us most convenient formulas. And we had the expressions for the tangent vectors r dot and phi dot of the principal null directions. And this is what I just write here. And I think this was r squared plus a squared. I check in a minute if it's right. And this was a. And then I have to normalize, of course, to make it into a unit vector. And the normalization is what? Here I have it. Rho times root delta. Oh, because of dimensional reasons, I should have a c here, dt over c. That's something with a which gives the right dimension. And then I have here rho root delta. So this is my E naught. And then I have to choose the spatial vectors E1, E2, E3, so that the whole thing becomes orthonormalized. And how do I do this? Well, there's an obvious choice for E3. I choose E3 in the, this is my polar my pole, south pole or north pole direction, yeah? So it's an obvious idea to choose this in a way that it points towards the black hole, yeah? So if I'm the observer here, I want to see the black hole in this direction. This is my E3 direction. And the black hole is in the direction of negative dr, yeah? In the negative radial direction. And the normalization is rho times root delta. Yeah, if you look at the metric, at the Kerr metric, you see in front of the GRR, you see delta over rho squared. So I just divide by the root of GRR, then I get a unit vector. So this is a fairly obvious choice. Then for the E1, I would choose something proportional to d by d theta. And I have to divide by 1 over root of g theta theta. And I think this was rho. Is that true? Yeah, that's true. And now the last one is fixed. It's a unique vector, unique up to sign, the unique vector which makes this whole thing into an orthonormal tetrad. Yeah? And it's of course a linear combination of dt and d phi because these two vectors are not orthogonal to each other. And what you find if you just construct a vector which is orthogonal to this here, then you get minus d by d phi minus a sine squared theta dt over c, and you have to normalize it, which gives rho sine theta. So I have chosen the signs in such a way that E1, E2, E3 is a right-handed system. Yeah? So E1 points downward, theta is this coordinate, so it points down. Then E2 points in the negative phi direction, and E3 points towards the center. So this gives a right-handed system indeed. So that's my basis. So, which coordinatizes my celestial sphere. Yeah? I'm sorry? There are no big zetas in this equation. Everything are small zetas. Yeah, these are the coordinates on the base manifold. Yeah? I construct a basis on my manifold. The basis is given in terms of Breuer-Lindquist coordinates, and of course the basis vectors they involve the Breuer-Lindquist coordinates where I am. Yeah. So what I have to insert for the r here and for the theta here is the r and theta coordinate of the observer at this event. At this event, I have r and theta. Yeah. It's a small theta. Yeah. So maybe we could put an index O here for observers, and this everything would be at RO theta O, RO theta O. Here's another one. RO theta O, RO theta O. Okay, and with the help of this equation here, I can now relate these coordinates on the sky. Well, in the first place, with the derivatives of my tangent vector given in terms of t dot, phi dot, r dot, and theta dot. But t dot, phi dot, r dot, and theta dot are given in terms of the constants of motion by the equation of motion. So if we do these two steps, then from this equation we get a relation between the celestial coordinates and the constants of motion. So that will be the goal for the following calculation. We want to express the celestial coordinates. You give me a theta and a phi, a big theta and a psi in the sky. That's a certain direction in the sky. And I want to tell you what are the constants of motion, L, K, and E of a light ray which comes from this direction. That's what I want to calculate now. In order to do this, I think I need more space for this. Do it on the next board. Well, let's see. If we want to solve for the angles, of course, I first solve for the expressions which we have in front of E1, E2, E3. So let me try to solve for sine theta cosine of psi. Well, from the expression up there, I read that this is G times E1K, right? If you calculate this, the scalar product of E1 and K, then you see on the, oh, I forgot the n, 1 over n. Then I get precisely this. Yeah? Okay, but E1, I have an expression for E1 here. So I use this expression here. Or rather, no, I do it the other way around. I insert this expression for K up there in the left part of the equation. Then I get 1 over n GE1. Well, E1 involves only the theta. E1 involves only the theta. So from the K, I get theta dot d theta. Is that true? Let me see. Oops, it looks funny. Okay, I think I missed part of my notes. Let me see if I can manage to do this.
One question.
Yeah.
The K shows the direction of coming light, or
K is a tangent vector to the light ray. Yeah. So I write this vector K, which is given in terms of my Breuer-Lindquist coordinate basis. I write this as a linear combination of this tetrad, and then I equate these two expressions, and yeah, then I just calculate.
What is K normalized?
What do you mean by normalized? It's a light-like vector. I know that it is a light-like vector. This is a light-like vector. And if this is supposed to be pointing in the same direction as this, then I must, then the only possibility is that there is a factor in front of it. But I wouldn't call this a normalization. These are normalizations, yeah? E1 is normalized to -1, this to +1, to +1, to +1. But this has Lorentzian length 0. So what does it mean to normalize a vector which has Lorentzian length 0, yeah? It just means that the two things are parallel to each other. That's why I have this, this factor there.
And then does the dot still refer to the conformal time?
The dot. What is a dot? Good question. What is a dot? What is a dot? The dot is derivative with respect to an affine parameter. Yeah? I briefly mentioned the possibility of introducing the Mino time. Then we would write this as, say, r prime squared, the whole expression, and then the derivative, this prime derivative, would be the derivative with respect to the Mino parameter. But here I'm using just the ordinary affine parameter with which we started. The dot for light-like geodesics refers to an affine parameter with respect to my given Kerr metric. For time-like geodesics, we use proper time, which is a particular affine parameter. Okay, so let me see if I can manage to do this. So this would be theta dot over n. E1 d theta, E1 is this here. This gives 1 over rho g theta theta. And g theta theta is rho squared, right? So this gives rho over n theta dot. No, sorry, this is rho squared, right? This is rho squared. G theta theta is rho squared. Yeah, that's much better. Because.
No.
I'm sorry?
It's got a rho in the denominator.
Right. Yes, this is rho squared. Oh, yes, it's only rho. Yeah. Okay, but I want to have a rho squared, so let me leave it this way. Because rho squared theta dot I can express in terms of the constants of motion up there. Yeah? Because this is just the square root of k minus L over sine theta minus A over C sine theta times E. And okay, this already gives me some information of how the angular coordinates on the sky are related to the constants of motion. I have this normalization factor n still in it. I have to kill this later. We have to talk about how to do this because I don't know the n. So then the same thing for sine theta sine psi. Then I have to multiply with E2, right? So this gives G E2 times K 1 over n. So this is 1 over n G E2. And K is what? K is E2 has a phi and a t coordinate, so I need only the t and phi coordinates from the K. So this gives me t dot dt plus phi dot d phi. Okay, this expression becomes a little bit longer. So I have, let me write 1 over n in front of everything. Then I have t dot, and then let me see what I get. T dot times g E2 d by dt. So I have to multiply this with d by dt. This gives a minus g phi t, or t phi, which is the same, minus a sine squared theta gtt divided by c. And then I have to divide by this denominator, rho times sine theta. So this is this term, GE2 times d by dt. And then the term with phi dot. With phi dot, this gives E2 times d by d phi. This gives minus g phi phi minus a sine squared theta gtt by c rho sine theta. Oops. Okay, and now let me see.
Excuse me?
Yeah?
In the first line, where has the square gone?
Where was the square?
K minus the stuff squared.
In the first line.
Rho to the 4 times theta dot squared.
Yes. I took the square root here.
But you took the square root of
I think that's correct.
Some.
So the square of this here is what is under the square root.
No,
Not?
at least it's differently on the blackboard.
Oh, I forgot the bracket. And this square. Now I know what you mean. Thank you. Thank you. Yes, yes. Yes, I just copied the term improperly. Yes, thank you very much. Okay. And now I'm really curious if this works out the way I hope it will. Namely, if I combine these two terms, then I get what? I get minus t dot gt phi. Oh, very good. I think this works. G phi phi divided by rho sine theta. And if I combine these two terms, I have minus a sine squared of theta t dot gtt. I have a 1 over c here, 1 over c and a rho sine theta in the denominator, plus phi dot wait a minute, are the coefficients correct? Here I multiply with t, so this is gt phi gtt. Here I multiply with phi, g phi phi, this is wrong here, this must be a gt phi. Yeah? I multiply with d by d phi, so both things must have an index phi. Phi dot gt phi, very good. And our question to the audience. Does this sound familiar to you? This expression in the numerator here and this expression here in the numerator? Anybody recognizing this expression? Remember how we introduced the constants of motion E and L? They were derivatives of the Lagrangian with respect to t dot and phi dot. And these derivatives give precisely these expressions. So this is minus E and this is L. Yeah? So what we get is 1 over n. I think everything has a rho sine theta. And then I have here, this is minus E. No, with the minus sign it is plus E. It is plus E with a minus sign. And here I have, no, the other way around. Here I have the phi in both things. This is minus L. Sorry, nonsense. This is minus L. Derivative with respect to phi. And this is derivative with respect to t. So this is, there's a minus sign, so it is plus E over c times a sine squared theta. And the last one which we need is the equation for cosine of theta. This is g e3k 1 over n. This becomes fairly simple. The only component which gives something different from 0, E3 is proportional to d by dr, so I only need the r component. This is r dot d by dr. And this is 1 over n. So E3 is minus rho over root delta. Minus rho over root delta. I have an r dot here. And GRR is rho squared. Wait a minute. GRR is must be the square of the inverse. Must be delta over rho squared. Oops, do I really have a rho squared in the denominator? Oh wait, no, this rho is wrong. Look, E3 is minus rho divided by rho delta. So I have one rho here, right? E3 is rho divided by root delta. And then GRR is rho. GRR is delta divided by rho squared. I think that's it. But I would need another rho here. So I write this is minus root delta, delta divided by root delta. I have an n in the denominator. And I have, I want to write here r dot rho squared, Then I need a rho cubed in the denominator, if I'm not mistaken. And r dot times rho squared I can introduce from the expression up there. So this is minus root delta divided by n, rho cubed, and r dot rho square I copy from there is a square root minus k delta plus r squared plus a squared, no square, sorry, e over c minus al, and the whole thing squared. Okay, these are the, oops, are the three equations. And yeah, how do I do this? So from the first two equations I get the tangent of psi. If I divide this by this, I get the tangent of psi. Then the n cancels, right? I don't know the n, so I have to get rid of the n. So I get minus L plus EC over A sine squared theta divided by, let me write the n and then I cancel it out. And I divide by the cosine term. This is this term here. I divide by this, so I get rho n in the numerator, root k minus L sine theta minus a over c sine theta e squared. Oops. So this gives me the tangent of psi in terms of my celestial coordinate, of my constants of motion, sorry. These are the celestial coordinates. Gives me the celestial coordinates in terms of the constants of motion. And what do I do in order to get theta? In order to get theta, I can divide these two expressions by each other, for instance. So then I get tangent of theta sine psi is this divided by this, right? So I get the same expression, minus L plus E over C A sine squared theta, rho n. Here the n cancels, right? That's the essential thing because I don't know the n. Yeah, I have to get rid of the n somewhere, somehow. N rho sine theta. No, this is nonsense here, right? This is nonsense. This is this term there, and I divide by this was this term, and I want to divide by this here, right? So I want to divide by root delta n over rho cubed, and I have the square root in the denominator, minus k delta plus r squared plus a squared e over c minus al squared. Oops, and now we are done. And rho squared. Yeah, with these expressions, we know, if you tell me the constants of motion, we have a light ray with constants of motion L, E, and K. And we are at the position of the observer. So here I have to insert RO and theta O. RO and theta O. Well, actually, wait a minute. This expression depends only on theta O. RO doesn't occur. Yes, there's no R coordinate here in this expression, and this depends only on RO. That's quite funny, actually.
Choose the minus.
I'm sorry?
Is it the minus of the cosine theta term?
A wrong sign somewhere. Cosine theta. I overlooked this minus sign. Yeah. Yes, thank you. So then it should be here also. Yes, you're right. Okay, so you give me E and L and K for your light ray. Then I know at which point in the sky I will see this light ray. This gives me the coordinates in the sky. Conversely, if I give you the coordinates in the sky, actually this can be solved for the constants of motion, actually for K over E squared and L over E, for these two combinations. And then you you know the corresponding coordinates. And now we can construct the boundary curve of the shadow. The boundary curve of the shadow is given by light rays, which approaches our spherical geodesics. And we know the constants of motion for the spherical geodesics. Where are they? They are here. They are here in the bottom. Oops. So let's call this equation here, I don't know, S1, and this S2. If we let here the coordinate, this is not the R at the observer. This is the R coordinate of the spherical geodesic. Yeah, so I don't put an index O here. It's a different R. Yeah, it's the R of the limiting curve. So let this coordinate R here run over this region here, over all allowed radius values for the spherical light-like geodesics. And plug these expressions for K over E squared and L over E into these expressions here. Then you get a curve on the sky. You see? So with S1 and S2. This gives a curve on the sky. And the curve is given in the form theta of the curve parameter R. This R here, this is a curve parameter. It ranges over this interval. And psi over R. And this gives a curve on the sky, which is a boundary of the shadow. So this is a fully analytic formula for the boundary curve of a shadow in the curve spacetime for an observer at arbitrary coordinates RO and theta O. Well, arbitrary, of course, outside of the horizon. Yeah. So of course, this is not a time-like vector behind the horizon. Yeah. We have to be outside of the horizon, of course. Otherwise, we wouldn't see a shadow. Yeah? If I'm inside the black hole, I cannot see a shadow of the black hole, of course. But I can be in the ergo region. Yeah? I can be anywhere outside of the outer horizon. And yeah, the question is, how do these curves look like? So you can do this. You have here the constants of motion parameterized by R. Plug this into this expression, get theta and psi coordinate parameterized by R, and you get curves on the sky. And what you get is, you get something like this. So the plot will be something like this here. So you have here the psi coordinate. The psi coordinate is an azimuthal coordinate. So this is the direction towards the black hole. This is the direction towards the black hole. And here is your theta coordinate. It's kind of a radius coordinate, yeah? You look at the black hole, that's the theta coordinate. And this is the psi coordinate, which goes around in this way. And if you plot this curve, you get something like that. So you get something which, if A is in this range here, if A is in this range, you get something which on one side looks more or less like a circle, but on the other side it is flattened. Yeah? And this is easy, so it's no longer a circle. It's no longer a circle. And this is actually easily understood because on the black hole is rotating. So it carries the light-like geodesics with it. So the term which is used for this is that the black hole drags the light rays. Yeah, it drags the light rays with it. So this gives an asymmetry with respect to these directions. So in one direction, the shadow it extends farther away from the center than in the other direction. And this effect becomes extreme if this limit A equal m is reached. Then you have something here which is almost flat, yeah, on one side. So this is for an extremal black hole. And yeah, that's what we expect to observe. So we will do on the next problem sheet, we will discuss this a little bit further. And we will actually calculate the radial and the horizontal diameter of this for the black hole at the center of our galaxy. Well, the order of magnitude is similar to what we have done for the Schwarzschild case, yeah? So it will be still the 50-something microarc seconds diameter, but there's a certain difference between the vertical and the horizontal diameter now. And what's very, very important and very surprising, actually, which can be read from these formulas here. If we analyze this carefully, then you see that the shadow is always symmetric with respect to the horizontal line, which is very surprising. Well, if you're on the equatorial plane, if theta always pi half, then you would expect the thing to be symmetric. But if you are off the equatorial plane, actually you would not expect the shadow to be symmetric, but it turns out to be. And I have no geometric intuitive explanation for this, it just comes out of the calculation. So if we observe the shadow, and if we see that it is symmetric with respect to the equatorial, with respect to this horizontal line, this does not mean that we are on the equatorial plane. Actually, that's a question which is vividly debated in particular under radio astronomers. They have seen some indication that the thing at the center of our galaxy has not the spin perpendicular to the equator, to the disk of our galaxy. There are some indications, at least some radio astronomers claim that they have seen some indication that it has a considerable inclination. So this would not be visible as an asymmetry in the shadow, which is somewhat surprising, I would say. And there's another thing I should emphasize. We have calculated this for a particular observer, for an observer with this velocity. If you move with respect to this observer, then of course you have an aberration effect. Yeah, then the sky is distorted just by aberration. Remember aberration from special relativity? If one observer sees something in the sky and another one which has a relative motion, then you would see something different. And the effect is that in the forward direction, everything is compressed, demagnified, and in the backward direction, it is magnified. So if you move away from a black hole and look out of the back window of your rocket, then you would see the shadow enlarged. And in principle, the magnification could be arbitrarily big. So if you move with a relative velocity with respect to this observer, which comes very close to the velocity of light, then the shadow would be really big in the sky. Yeah? But you must be really close to the speed of light. Even with, I don't know, 95% or so, the effect is still fairly small. It becomes really palpable for, I don't know, 99.9% or something like that. Then you have magnification factors of 2 or even more. Yeah? And this is what you can draw out of this calculation. I think I have to stop now. And we will continue with these things in the next worksheet, as I said. And on Tuesday, I will then talk a little bit about time-like geodesics in the Kerr space-time. So it's time now for the tutorial. So I say goodbye to everyone who's watching, and we continue among ourselves.